Imagine standing in a silent room and suddenly realizing that everything you were taught about how the world began was actually just a placeholder for a much stranger reality. For nearly a century, astronomers and physicists have operated with a very specific set of rules called the Standard Model. It was our cosmic rulebook, explaining how the universe expanded from a hot, dense point and how the first stars and galaxies slowly flickered into existence over billions of years. But the James Webb Space Telescope, a $10 billion engineering marvel currently floating 1 million miles away from Earth, it has captured objects that are so massive, so old, and so mature that according to our current understanding of physics, they shouldn't exist. They are the universe breakers, galaxies that formed almost immediately after the Big Bang but look like they've been aging for eons. We are exploring the image that breaks physics, the mystery of the impossibly early galaxies, and why we might have to rethink the age and the origin of everything we've ever known. To understand why these images are such a big deal, we have to talk about how we thought galaxies were born. The Big Bang happened about 13.8 billion years ago. For the first few 100 million years, the universe was a dark, soup-like fog of hydrogen and helium. Gravity had to work slowly, pulling these gas clouds together until they grew dense enough to ignite the very first stars. These stars were supposed to be monsters, huge, bright, and short-lived. Eventually, these stars would cluster together to form small, messy, toddler galaxies. Over billions of years, these toddlers would merge and grow into the majestic spiral galaxies like our Milky Way. Messy toddlers. It found 6 massive, fully mature galaxies that contain as much mass as the Milky Way does today. It's like looking into a nursery and finding a group of 6-foot-tall adults in business suits sitting in the cribs. It simply doesn't fit the timeline. The lead researchers analyzing this data have used words like impossible and panic to describe their initial reaction. When they first saw the red dots in the deep field images, they assumed they were looking at a mistake or a glitch in the sensors. But the data was consistent. These galaxies are redshifted, meaning their light has been stretched by the expansion of the universe as it traveled across the void for over 13 billion years. The further the redshift, the older the object. These red monsters are sitting right at the edge of the observable beginning, yet they are packed with old stars. If the Standard Model is correct, there wasn't enough time for this much matter to accumulate. There wasn't enough time for the gas to cool down and collapse into stars. It's as if the universe hit the fast-forward button for the first few 100 million years, doing 1 billion years of work in a fraction of the time. This discovery points to a massive hole in our understanding of dark matter. According to our current physics, dark matter acts as the scaffolding of the universe. It provides the gravitational glue that helps normal matter clump together to form galaxies that fast. This means either dark matter works differently than we thought. Some theorists are suggesting that the early universe might have been fueled by dark stars, massive objects powered by dark matter annihilation rather than nuclear fusion. These dark stars could have acted as seeds, allowing galaxies to grow at an accelerated rate. But even that is a radical departure from the Standard Model. We are essentially looking at a cosmic construction site where the buildings were finished before the foundation was even poured. The James Webb Telescope is unique because it sees in infrared. Unlike Hubble, which mostly saw visible light, Webb can peer through the thick clouds of cosmic dust that hide the early universe. This is why we are seeing these things now. Hubble simply couldn't see the red monsters because they were shrouded in the shadows of the past. Now that the veil has been lifted, we are forced to confront the reality that the early universe was a much more violent and productive place than we imagined. It wasn't a slow awakening. It was a sudden, massive explosion of complexity. This challenges the very idea of cosmic inflation, the period of rapid expansion that was supposed to smooth everything out. If the early universe was already this lumpy and structured so quickly, our models of the Big Bang might be missing a crucial chapter. Another baffling observation from Webb involves the metal problem. In astronomy, anything heavier than hydrogen or helium is called a metal. These elements are created inside the hearts of stars and then released when those stars reach the end of their lives. Therefore, the very first galaxies should be metal poor because there hadn't been enough generations of stars to cook up heavier elements like oxygen, carbon, or iron. But Webb has detected significant amounts of these elements in galaxies that are far too young to have them. This suggests that stars were forming, living, and finishing their cycles at a rate that is practically impossible under the standard model. It's as if the first stars were living 1,000 years in a single day. This metal-rich early universe suggests a level of star-forming efficiency that we have never seen in the modern world. As we look deeper into the Webb images, we also find the Great Wall problem. Astronomers have found massive chains and filaments of galaxies stretching across millions of light-years in the very early universe. The standard model says it takes a long time for these large-scale structures to form. Gravity is a relatively weak force, and moving entire galaxies into a coordinated line should take billions of years. But Webb sees these cosmic webs already in place when the universe was just a tiny fraction of its current age. This hints at the possibility that the universe might be much older than 13.8 billion years. Some researchers are cautiously suggesting that the universe could be twice as old, perhaps 26 billion years. This would solve the time problem by giving galaxies more time to grow, but it would completely break our current measurements of the expansion rate of space, known as the Hubble constant. The James Webb Telescope has also spotted black hole monsters where they shouldn't be. At the center of almost every galaxy sits a supermassive black hole. In the modern universe, these black holes grow slowly by swallowing gas and stars over eons. But Webb has found active galactic nuclei powered by massive black holes in the very early transition period of the universe. These black holes are already millions or even billions of times the mass of our Sun. How did they get so big so fast? Under the standard model, a black hole starting from a single star would take a very long time to reach that size. This suggests direct collapse, black holes, where giant clouds of gas skipped the star phase entirely and collapsed straight into a black hole. While this is a fascinating theory, we have never actually seen it happen, and it requires conditions that the standard model says were very rare. The implications for our understanding of the beginning are profound. If the standard model is broken, it means our story of how we got here is incomplete. We might be living in a universe that has gone through multiple cycles of expansion and contraction. The Webb images are like a mirror being held up to our own ignorance. The universe breakers are not just dots on a screen. They are a call for a new Einstein, a new Newton, someone who can look at this data and find a pattern that unites these impossible objects with the laws of nature. One of the most exciting and terrifying concepts being discussed is that our measurement of time itself might be skewed. If the universe is expanding at different rates in different directions, a phenomenon called anisotropy, then our calculations of age based on light travel would be wrong. Webb has provided some evidence that the early universe was much more chaotic in its expansion than we thought. This could mean that the light we are seeing from these galaxies didn't take 13 billion years to reach us, or that the years themselves were different in the early. The cosmic dawn was supposed to be a quiet period, but Webb shows us it was a blazing, crowded, and highly structured era. This has led to the early galaxy problem. Some scientists are now looking into modified gravity theories, like Mendel-modified Newtonian dynamics, to see if they can explain the rapid formation of these galaxies without the need for massive amounts of dark matter. If gravity was stronger in the early universe, or if it behaves differently across vast distances, it could explain why matter clumped together so quickly. But shifting away from general relativity is one of the most radical steps a physicist can take. It would mean that Einstein's masterpiece is only an approximation, a local rule that doesn't apply to the whole. Let's talk about the tension in the Hubble constant. For years, there has been a discrepancy between how fast the nearby universe is expanding and how fast the early universe was expanding, based on the cosmic microwave background. This is called the Hubble tension. Instead, Webb has confirmed the tension. It has shown that the discrepancy is real and even larger than we thought. This suggests that there is new physics lurking in the expansion of space, perhaps a form of early dark energy that gave the universe a kickstart in its first few million years. This would explain the fast galaxy formation, but it adds a whole new level of complexity to our cosmic models. Webb has also captured images of stealth galaxies. These are galaxies that are almost completely invisible to every other telescope, because they are so far away and so redshifted. Webb's mid-infrared instrument, MIRE, has found that the early universe was actually crowded with these stealth galaxies. This means the universe was much busier than we thought. Every time we point Webb at a dark patch of sky, it finds thousands of galaxies. This suggests that the total mass of the early universe might have been underestimated. If there is more stuff out there, It changes our calculations for the total energy density of the cosmos, which in turn affects our predictions for how the universe will eventually end. The images we are seeing are not just pictures. They are datasets. Astronomers use a technique called spectroscopy to break the light from these galaxies into a rainbow. This rainbow tells them exactly what those galaxies are made of, how fast they are moving, and how old their stars are. If population 2 stars existed just a few 100 million years after the Big Bang, then the population 3 stars must have lived and died almost instantly. This pushes the first light event even further back in time, into a region that Webb can barely see. We are reaching the absolute horizon of our knowledge. This brings up the cosmic dark ages again. We used to think this period lasted for hundreds of millions of years. But if galaxies and black holes were already mature by 300 million years, then the dark ages must have been incredibly short. The universe went from a state of neutral gas to a state of ionized, star-filled space in the blink of a cosmic eye. This rapid reionization is another mystery that the Standard Model struggles to explain. It requires a tremendous amount of high-energy radiation to ionize the entire universe. Where did it all come from? If there weren't enough stars yet, maybe the black hole monsters were the ones doing the heavy lifting, stripping electrons off hydrogen atoms across billions of light years. The Webb telescope is also looking at gravitational lensing. This is when a massive foreground object, like a cluster of galaxies, acts as a natural magnifying glass, bending the light of even more distant objects behind it. Webb has used these cosmic magnifying glasses to see individual stars in the early universe. One of these stars, nicknamed Earendel, is the most distant star ever seen. While Earendel fits the timeline better than the red monster galaxies, the sheer brightness and size of these early stars are still pushing the limits of stellar evolution models. They are simply bigger and more energetic than anything we see in our neighborhood today. Some physicists are now proposing that we are seeing evidence of a variable speed of light. While this is a highly controversial idea, if the speed of light was faster in the very early universe, it would solve many of the horizon and timing problems we are seeing. It would explain how different parts of the universe could communicate and coordinate their structures so quickly. However, the speed of light is the cornerstone of almost all modern physics. If you change that, you have to rewrite everything from E=mc² to the way atoms hold together. This is why the Webb discovery is so disruptive. It forces us to at least consider the unthinkable. We also have the small-scale crisis. While the Standard Model is pretty good at explaining the big stuff, like the overall distribution of galaxies, it fails when we look at the small scale, like the number of satellite galaxies around the Milky Way. Webb is helping us see smaller, dimmer galaxies in the early universe, and it's finding that there are too many of them. This suggests that gravity was more efficient at creating small things than our dark matter simulations predicted. It's like a sculptor who is much better at making tiny details than he is at the large statue. This discrepancy points to a fundamental misunderstanding of how cold dark matter behaves on a local level. Webb has also been looking at protoclusters, groups of galaxies that are in the process of merging to form the giant clusters we see today. It found a protocluster of 7 galaxies that were already tightly packed together just 600 million years after the Big Bang. These galaxies are zooming around each other at incredible speeds. To keep such a busy, high-energy group together, you need a massive amount of gravity. This again reinforces the idea that the scaffolding of the universe was in place much earlier than we thought, rather than getting ready as it went along. What does this mean for the average person? It means we are living through a scientific revolution. Just as people in the time of Galileo had to accept that the Earth wasn't the center of the universe, we might have to accept that our Big Bang story is just a simplified version of a much more complex reality. The images from Webb are a reminder that the universe is not obligated to make sense to us. It follows its own laws. And our job is to be humble enough to change our minds when the evidence speaks. These impossible galaxies are a gift to science because they show us exactly where we were wrong. The universal expansion itself is under fire. Some researchers are using Webb to look at standard sirens, events like merging neutron stars to measure distance in a new way. If these measurements continue to conflict with the Standard Model, we might find that the universe isn't expanding into empty space, but is rather part of a higher dimensional structure that we are only seeing a slice of. This would bridge the gap between general relativity and quantum mechanics, the two pillars of physics that currently refuse to talk to each other. Webb might be the tool that finally forces them to reconcile. Webb is also looking at the Great Attractor and other massive gravitational anomalies. By looking back in time, it can see if these anomalies were present from the beginning. If the universe started out with these massive pulls already in place, it suggests a non-random beginning. It points to a phase transition in the early universe, where space-time itself might have changed its properties, much like water turning into ice. If the early universe went through such a transition, it would explain why structure appeared so suddenly. The universe breakers would just be the first crystals of matter forming in the cooling cosmic sea. The data is still coming in. Every week, new papers are published as teams around the world analyze the data from Webb's latest observations. The panic of the first few months has turned into a scientific ferment. Engineers and physicists are working overtime to see if there is any way to save the standard model by tweaking the variables. Maybe the galaxies aren't as massive as they look? Maybe the star-forming light is just very bright? But so far, the simplest explanation is that something is fundamentally different about the early universe. Occam's razor suggests that the model is the problem, not the data. This journey of discovery is just beginning. James Webb has a planned mission life of 10 to 20 years. We have only been looking at these images for a relatively short amount of time. If it found universe breakers in its first year, imagine what it will find in year 10. We might find the very first stars, the population 3 stars that are made of nothing but primordial gas. We might find the shadow of the first black holes. We might even find evidence of cosmic strings, one-dimensional defects in space-time that could carry the mass of entire mountain ranges in a single millimeter. Webb is also exploring the atmospheres of exoplanets in our own galaxy, looking for signs of life. While this doesn't break physics in the same way, the discovery of life elsewhere would be a different kind of revolution. It would show that the laws of biology are as universal as the laws of physics. If we find that the universe breakers are full of life-supporting heavy elements, as we wrap our minds around these images, let's remember the scale. The deep field images from Webb cover a patch of sky about the size of a grain of sand held at arm's length. In that tiny grain of sand, there are thousands of galaxies, each with billions of stars. The universe breakers are just a few of the stories hidden in that grain. James Webb hasn't just shown us the past, it has shown us the future of physics. The standard model has been a good friend to us. It has explained the stars, the planets, and the atoms in our bodies. But as we push into the frontier of the cosmic dawn, we are finding that our friend has limitations. The images that Webb is sending back are not a failure of science. They are its ultimate success. They are proof that our tools are finally good enough to challenge our assumptions. The universe breakers are the beginning of a new chapter in the human story, one where we recognize that the universe is far older. Think about the light of those galaxies. It has traveled through the void for 13 billion years, passing by countless stars and through vast tracts of empty space, just to hit a mirror the size of a tennis court and be converted into data that we can see. That light is a message from a world that existed before the Earth was even a cloud of dust. It is a message that tells us to keep looking, to keep questioning, and to keep being amazed. The standard model might be breaking, but our curiosity is stronger than ever. The James Webb Telescope has changed our place in the universe. It has taken us out of the nursery and shown us that the grown-ups were already there from the start. It has shown us that the beginning was a lot more like a grand opening. As we continue to decode the red-shifted secrets of the deep field, we are not just looking at the stars. We are looking at the very fabric of reality being woven in real time. The new physics is coming, and it looks more incredible than anything we could have written in a textbook. So, the next time you look up at the night sky, realize that you are looking at a masterwork that we are only just beginning to understand. The James Webb Telescope is our new set of eyes, and what it's seeing is a universe that refuses to be simple. It's a universe that is breaking our rules. But in doing so, it's giving us a chance to discover the real laws of the cosmos. The standard model might not survive the decade, but the truth that replaces it will be even more spectacular. The universe breakers have spoken, and they are telling us that the adventure of discovery is only just starting. Stand tall, stay curious, and keep your eyes on the infrared light of the past. The future of science is happening right now, one impossible image at a time. This is the era of Webb, and the rules are about to change forever. The cosmic dawn is here, and it's much brighter than we ever thought possible. Let's see where the light leads us next.